It's time to take a look at confidence intervals. As before, we will give an overview and demonstrate some of the most common methods of deriving confidence intervals, some of the properties, and then later on we will add some examples and special cases. So the handout here is from the usual tutor web, and it's a bit more rough than many of the earlier ones, so you may want to consult the actual book by Casella and Berger. But basically, we know that, for example, we start by an example. We know that if we have a random sample from a normal mu sigma squared, then we can subtract the mean and divide by the standard deviation of the sample mean. And we know that we will get a new random variable which has a normal 0-1 distribution, so for fixed mu and sigma. And this leads to a general or a common method of inversion, where we now know that the normal 0-1 random variable has a certain probability of being between the two extreme values, or between two values in the normal distribution, the outer alpha over 2 cutoff points. And so the probability then of this random interval being encompassing mu becomes 1 minus alpha. So the random set has a 95% probability of covering mu if alpha is 0.05. Now, once we have actual data, so we have outcomes of these random variables, we can compute the corresponding interval, and it's just a realization of this set. So we start with a random set, and then we plug in data and we call that a confidence interval, or a confidence set in a general case. Now, and you've got to be very careful with the interpretation here. There is no probability anymore in this regarding this interval. It's just a couple of numbers. So we simply claim that mu is in the confidence set. And the reason we claim this is that we know that this process of generating data, if that holds, then these sets will, in 95% of all cases, contain the correct value, if the assumptions hold. So we can also convert tests, and we've done this in elementary stats courses, where if the null hypothesis is true, then we have a random variable which has a normal 0-1 distribution, and we can then convert the test. This really corresponds to starting with the test statistic in the middle here, and then converting that to the confidence interval. And you'll note that we're using the notation z sub alpha to denote the lower alpha quantile, and correspondingly z1 minus alpha over 2 then is the value such that there is 97.5 probability, if you like, below the z value. So the probability corresponds to the subscript. And textbooks do this differently. Now, next we can take the general case. If we have a test function for testing theta equal to a constant, then we can look at the collection of all of these tests, and we can write c of x as the collection of theta such that phi naught of x is equal to 0, and this is supposed to be little x. So we define this for all possible outcomes, and it then turns out that if these are all level alpha tests, then the set c of x has coverage probability at least 1 or equal to 1 minus alpha. If the size alpha test, then the set has coverage exactly 1 minus alpha. Otherwise, if they're level alpha test, then it has probability at least 1 minus alpha. The proof is completely trivial because of the definition of the confidence set. And now we can talk about confidence intervals and interval estimators as the obvious things. And we can also talk about the confidence of the set. That should be C of lower x, and the coverage probability is the corresponding actual probability. So if we have a certain coverage probability, and we call this the confidence of the set, and that's supposed to be a lowercase x. Now, a location family is something we defined before, and it's a family with a sort of shift parameter. The density for a general mu is some null density at evaluated x minus mu, and we can then look at the quantity x minus mu, and this quantity, the CDF of this quantity, is somewhat obviously a quantity which doesn't depend on mu, and if we differentiate this, then obviously the mu's cancel. So, but you'll be careful here that this is not a random variable, and it's not an unknown parameter because it contains both. So we call this a random quantity typically, or a quantity, and a quantity which doesn't depend, whose distribution doesn't depend on the original parameter, we call a pivotal quantity. In Icelandic we call this vendihending on a good day. And similarly, for a scale family, we need to divide by the quantity and we get exactly the same result. Now, there are some statistics which play a special function here, and these, for example, statistics which are linear, and they may be linear only up to the absolute value of the scale parameter, but that's fine. We're only looking at positive sigmas anyway. So some of these are shift functions, others are completely linear, and some of them have just the scaling property. And we have a whole sequence of these, which then are all pivotal quantities. We can take the median, or we can take the mean, we can take the largest value, the smallest value, the median, and due to the properties of each one, for example here number 4, the smallest value minus mu divided by sigma is the same as the smallest of the values xi minus mu divided by sigma. And since xi minus mu divided by sigma has a distribution which doesn't contain sigma or mu, we also see that the minimum of them doesn't contain sigma or mu, and therefore x1 minus mu, or the minimum minus mu over sigma, is a pivotal quantity. And now, of course, the reason for this is that we want to take this general statement about a pivotal quantity, find bounds which give a probability equal to 1 minus alpha, and we know that this bound is going to be free of the parameter because it's a pivotal quantity. And then we want to somehow invert this or pivot this to get a statement on the or get a set which contains theta. And there are several examples of this. You've done some of this, we've already done one. Here are some more, and we have to be a little bit careful with exactly which quantities we choose. We cannot choose a quantity such as the mean minus the median over the standard deviation, because this doesn't involve the parameters, and it also has a distribution free of the parameters. So it has no information. It's an ancillary statistic in a location scale parameter. But we can use S over sigma to make inference about sigma in a location scale family, and we can use x minus mu to draw inference on about mu, and so forth. We also sometimes want to seek short intervals, in which case we start by saying we want to somehow or other choose A and B, which provide us with a coverage probability, and then we want to choose A and B so that the confidence interval becomes as short as possible. And this usually becomes an exercise involving a Lagrangian or something similar. This is not too hard to do in certain distributions, and it's much harder in others. So here's some draft examples, and here is a whole bunch of more confidence intervals. Now, to take the case for the test statistics, we know that the confidence intervals has an appropriate coverage probability if the probability of coverage is to be a large X is 1 minus alpha, and we know how to invert tests to get this, there's an example here of the Gaussian test, which is a fairly trivial one. You could take the usual test for mu equal to mu naught, and then the usual test has this rejection region, so we can now look at the acceptance region and invert that to get our usual confidence interval. So all of this is fairly easy, and there's some more stuff here about pivotal quantities. Just be careful that sometimes there are typos in the text interchanging capital X and lowercase x. There's a way also to write this using set and set differences. For example, here we've taken the inverse of the point 0, so this becomes the acceptance region for the test, and then minus this inverts or rather flips the set around, so then and this should be the data or vector x shifted by the vector x, and there are really too many typos in this still to use it. This would work if this was the vector of means, for example, and this was a function of the mean, not of the entire data vector. And so on. A few more examples here near the end, so we'll let that be enough for now, and give hopefully some more examples later.